Hello everyone, welcome to GradDr. So far we have studied about the Newton's law of gravitation, which includes the gravitational force. Second, we studied about gravity and acceleration due to gravity. We have also talked about the relation between the acceleration due to gravity and the universal gravitational constant. In today's lecture, we will study about the variation of g, which is acceleration due to gravity, variation of small g, due to shape of the earth, height above the earth, depth and rotation of the earth. So how this acceleration due to gravity varies due to these four factors. Now let's talk about the variation in g with respect to in small g due to shape of the earth. So for this, first of all, we should know what is the shape of the earth. So shape of the earth is quite elliptical, like this. If we measure the radius along the equator side and pole side, then we can see that the radius of equator is greater than radius of the pole. We also know that since earth is an elliptical shape, or we can say ellipsoid because it is a 3D diagram, we know that semi-major axis is this one and semi-minor axis is this one. So from the relation between the small g and capital G, we know that small g is equal to gm by r square. Now if we will write this equation at equator, then at equator we will get GE equals to capital GM upon RE square. Let's give this equation 1. Now at poles it will be GP equals to capital GM upon RP square. Give this equation 2. Now if we see that from first and second, if we take the ratio GE upon GP, then it will be RP square upon RE square. Now we know that R equator is more than R poles. So G pole will be greater than G equator. And this value is nearly GP equals to G equator plus 0.018 meter per second square. This is the difference. So if we will say that there is a body of mass m mass m, then where will be the weight of the body is more? So weight is mg. Now if we will write wp, that means weight at pole, so it will be mg pole, and at equator we mg equator. Now since g pole is greater than g equator, so weight of the body at pole will be greater than weight of the body at equator. Now next we will see the variation of g due to height. Now consider Earth this is the center O, this is the radius R, and suppose a body is raised up to height h. This is h. So at the surface of Earth, we know that acceleration due to gravity is small g. At this height, the acceleration due to gravity is g dash. And let's give this distance as r, small r. Now, if we will write acceleration due to gravity at surface of Earth, acceleration due to gravity at surface of Earth, at the surface, then that will be the same formula which we were talking about. So small g is equal to gm by r square. Now since we have raised an object, or we have to measure the acceleration due to gravity at this height, then what will be the acceleration due to gravity? Since we have raised up to this height, so the distance will be this, in place of this r only, capital R, we will write small r square, or we can also say that small r is capital R plus h. So acceleration due to gravity at h height will be small g equals to capital Gm upon r plus h square. Equation second. Now from first and second, from equation 1 and 2, if we will take the ratio, so the ratio will be, sorry, there is one thing, this will be g dash. So the ratio g dash upon g, so g dash is gm by r plus h square, and g will be r square upon gm. So this gm will be cancelled, and we will get g dash equals to small g r upon r plus h whole square. This is equation 3. Now or it can be written as g, since small r equals to r plus h, so this can be written as g r upon small r square. This question 4. Now the main thing is, what should we conclude from this? So important points, if we will write. First, so as we go above the surface, G varies and it becomes G dash is directly proportional to 1 upon R square. That means its value decreases. Second, suppose if value of R is infinite, we have taken far enough the point out of the gravitational field of the earth, then this G dash will be 0. Why? Because we will see that the expression will become G dash G R upon infinity square, and we know that 1 upon infinity is 0. So that's why G dash will be 0. What is the physical significance? This means that the height up to which we have taken the value of a small g, at that height there is no influence of gravity, or the gravitational field of earth doesn't take place. Third point, if suppose small h is very much less than radius of the earth, that is h is negligible in comparison to r, then equation G dash will be G r plus h square, and it will become G, if we take r as common, so G1 plus h upon r square, this will be cancelled out, we will get G1 plus h by r to the power minus 2. Now if we will expand this from binomial theorem, then this will be G1 minus 2h upon r and some higher terms. These are higher terms. And why these higher terms will not be included? Because h is very much smaller than r, so the ratio of h upon r, or we can say the next term will be h square upon r square, this will be very much less. This will be less, very much less, and the further term will be cubic term. So we will remove this higher terms. So we will get G1 minus 2h upon r. Let's talk about the next point. Now, if h is very much less than r, then decrease in the value of g, in the value of g with height will be, if we talk about the absolute decrease, So absolute decrease is nothing but difference. So G minus G dash. Since the bigger term is small g, so we have written this here. So this will be 2hg upon r. We'll talk about the fractional decrease. So fractional decrease means we have to take the ratio of the absolute decrease divided by the original value. So this will be g minus g dash upon g, and this will be, if you will see this will be g minus g dash upon g, and g dash upon g, we see from this equation g dash upon g will be 1 minus 2h upon r. So this will become 1 minus 1 plus 2h upon r, and this will be cancelled out. So we will get 2h upon r. So the fractional decrease will be capital G small g 2h upon r. This fractional decrease is an important point. Sometimes these questions are asked in paper. Next, percentage decrease. So percentage decrease is nothing but fractional decrease into 100. So this will calculate the percentage. So that will be 2h upon r into 100, and this will be shown in percent. Now let's talk about the variation of G. Third one is variation of G with respect to depth. So variation of G due to depth. So for depth, we should be writing the expression of G not as Gm by r square but in the density form, that was 4 by 3 pi gr. We have talked this in the previous lecture. Because why we are taking this? Because due to depth, the density of the earth also changes. So suppose this is earth, and we take small g at radius r, and let's talk that here is some point where we have to calculate the acceleration due to gravity. So this is r, and let's suppose that here the acceleration due to gravity is g dash. So we will consider this part. So there is one thing. Can we say that density will be affected or not? So the answer is no. Density will not affect. Only mass and volume will be changed, and their ratio will be same, which is density. So if anyone asks that if we are taking small g at depth, then is there any change in the density? No, density will be same. If you will take a spoonful of earth, then density will be same. So density doesn't change. Density is a fixed quantity. Only the mass and volume changes. So now if you will write at depth d, this is, let's say that this is depth d, this much, step d. So acceleration due to gravity at depth d from the surface, that will be g dash 4 by 3 pi rho g r minus d, equation second. Now dividing both equation, one and two, we will get g dash upon g as 1 minus d by r. So how this 1 minus d by r came? If you will see, g dash upon g, that means 4 by 3 pi rho g r minus d, and this was 4 by 3 pi rho g r. So this term is cancelled out. This term we get only r minus d upon r, so this will be 1 minus d by r. So this is the expression. So this is the variation due to depth, or we can say g dash is equal to g 1 minus d by r. Now let's talk about some important points. So we see that value of g decreases with depth. That means going below the surface, the value of g decreases. And how does it decrease? So g dash will decrease as r minus d. Second, let's talk about at the center of the earth. Now next we will talk about the variation of g with the rotation due to rotation of the earth. So let's see the earth let's say this is the earth and this is the axis of rotation, let's say omega, the angular velocity, say omega, and here is some point P. So if a body of mass is lying at P, then we will resolve this and we will see this one, the mg, the centripetal force, will be at the center of the earth, the centrifugal force will be here, and their resolution will be like this, mg dash. Let's from here, r is the distance, and this lambda is the latitude. So if we say that for lambda, so at poles lambda will be 90 degree, because from here angle, if you will calculate from here, and at equator lambda will be 0. Now we know that as earth rotates, a body placed on its surface moves along the circular path, and hence it will experience a centrifugal force, since the earth is rotating and body is on the surface of the earth. So whenever a body is placed on the rotating surface of the body, then it experiences centrifugal force. When the body is attached to anything and it itself rotates, then it experiences the centripetal force. So centrifugal force is nothing but a pseudo force, and it is just a mirror part of the centripetal force. This we will talk in the mechanics lecture. So if it experiences the centrifugal force, its apparent weight will be less than its actual weight. There will be a decrease in the weight. Now, since the magnitude of centrifugal force varies with the latitude, at this point it varies with the latitude, so apparent weight of the body will also vary due to the latitude. Now, if we say that if a body of mass m is at point P, also we will define that, whose latitude is lambda, then we discussed that due to centrifugal force, actual weight of the body decreases, therefore the apparent weight will be less than the actual weight. So if we say that at point P the acceleration due to gravity is g dash, then the apparent weight, if we will resolve this, we will see that the mg dash will be equal to mg plus fc. Or, since this is written in vector form, if we will write this in the magnitude form, then this will be under root square of these terms, mg square plus centrifugal force square plus 2 times mg fc and the angle between them, so cos 180 degree minus lambda. Now, what is the centrifugal force? So for centrifugal force, we know that it is m omega square r, and this will be m omega square r cos lambda. So this small r will be the resolved part of the lambda. So r is r cos lambda. That is the base component. Or the horizontal component. This. Since this is r, this one is r, here is lambda, so the resolution part will be this. So r will be r cos lambda. Okay. Now, so we have written the centrifugal force. Now, coming back to this, so mg dash equals to under root, now this will be mg square plus m omega square r cos alpha square plus 2 mg m omega square r cos alpha and minus cos alpha. Okay. Since cos 180 degree minus theta is minus cos theta. In this case. Now, if we will solve this, we will get, now try to solve this one, we will get g dash equals to g minus omega square r cos square lambda. So it's basically, it will convert into an algebraic expression of a minus b whole square. So when this will come, see, a will be small g and b will be omega square r cos square lambda. So for the rotation, we got this expression, cos square lambda. Let's talk about the important points. So first one is, if we put lambda equals to 90 degree, that means at poles, then g pole will be g minus omega square r cos square 90 degree. So this term will be 0. So gp will be acceleration due to gravity. So there will be no effect of rotation at poles. You can also experience this in the playground So whenever we play at merry-go-round, which rotates like this, and we always fear of standing here, if you want to save yourself, then you should be holding this, the center part. The more closer you will be to the center, the more safe you will be. Otherwise, if you are standing at the extreme point, you will be thrown tangentially from the merry-go-round. So we have observed this, we all have played this game in the playground. So let's talk about this. There will be no effect of rotation at poles. Second point, now if we put lambda equals to 0 degree, then it is at equator, so G equator will be G minus omega square R cos square 0 degree. So this will be G minus omega square R, G equator. So from here we can say the effect of rotation, see the expression, the effect of rotation of Earth on small g at the equator is maximum. So the effect of rotation is maximum at equator. Now let's see the difference. G pole and G equator. So this will be R omega square, and its value comes nearly 0.034 meter per second square. Next point is, when a body of mass m is moved from equator to poles, that is, a body is moved from here to the poles, okay, from equator to pole, then the weight, increase in weight will be m gp minus ge, and this will be m omega square r, weight increase. Next, now weightlessness due to the rotation of the earth. Now we have already talked that the apparent weight decreases due to rotation of the earth. So if the angular velocity of the rotation of the earth, for which a body at the equator will become weightless, so we will calculate the angular momentum, for which the body at the equator will experience weightlessness. So we will calculate angular velocity omega, for which body will experience weightlessness. From the expression G dash G minus omega square R cos square lambda, for weightlessness or at equator we know that small g dash, we know that lambda is 0, and for weightlessness we will take g dash 0. So g minus omega square R.